This is Electrodynamics Introduction to Griffiths 4th edition. I am working back through and making chapter summaries for all of the first 6 chapters. I would consider this a 2-semester course. That's what we do. The first semesters are electric and magnetic fields, the first semester. So let's just go over the bare basic stuff in chapter 1. Chapter 1's on, it says vector analysis, but it's really mathematical methods of physics. There is a lot of stuff in chapter 1. After going through the first 6 chapters, I'm going to tell you the things you absolutely need to know. I'm not going to go over everything. Okay, so I got my little notes here. The first thing is vectors. I mean, there's a bunch of things with vectors. I'm not going to tell you exactly everything about them, but I can represent a vector as AX, AY, AZ in Cartesian coordinates, at X, Y, and Z components. And then you can do things like add vectors, A plus B. You can multiply by a scalar, A times A. You can take the dot product, A dot B. You can take the cross product, A cross B. So all those operations you should know. Now, the other ones you need to know are A hat. A hat, well, let's say a magnitude first. The magnitude of a vector in Cartesian coordinates, ax squared plus ay squared plus az squared, square rooted, and then the unit vector for a vector, a hat. This is the vector that's in the direction of a, but it has a magnitude of 1. So this is just going to be the vector a divided by the magnitude of a. You think, oh, that doesn't really matter. It matters. You already have seen some unit vectors. X hat is the vector 1, 0, 0. It's a unit vector in the direction of x. Okay. Let's go on to the next topic. Next, we have these 4 vector operations, vector derivatives. I'm going to call them vector derivatives. And they all deal with what we call the vector derivative operator. I like to call it del. Okay? So del is an operator in Cartesian coordinates. It looks like this. It's a vector. The partial with respect to x in the x direction, the partial with respect to y in the y direction, the partial with respect to z in the z direction. Now, in other coordinate systems, it looks way different, and we'll talk about that later. So I can take that and treat it just like a vector. I can operate this on a scalar because you can multiply a scalar and a vector. So suppose I have some vector, some scalar function f. F is going to be a function of x, y, and z. Let's say it's x times y times z, something like that. Well, I can take the gradient of this vector. So I can say the del f is the gradient. Oops, that looks bad. Well, it's the gradient. So I'm just going to take this operated on that, and it's going to be the partial. I'm going to get a vector result, right? Because I have a vector operating on that. I get the partial of f with respect to x, the partial of f with respect to y, the partial of f with respect to z. So I take a scalar function and give me a vector back, a vector function. If you're dealing with this in a map or something like this, this tells you the direction of change. If it's a hill, it's which way, how steep is the hill, and in which direction. That's the gradient. The next thing we have is called divergence. So now suppose I have a vector function, f of x, y, z equals f x, x hat, plus f y, y hat, plus f z, z hat. So these are functions of x, y, and z also. Well, the divergence is just going to be del dot f. So now I just do the dot product. So if I take this dot that, I get the partial of fx with respect to x, that's with respect, plus the partial of fy with respect to y, plus the partial of fz with respect to z. So the divergence basically tells you how a vector field diverges, right? So the classic case is point charges make electric fields that diverge from the positive charge and towards the negative charge. So that's that. Finally, we have, so I'm going to write these down over here. Let's keep a little list. So I have the gradient del of f. I have the divergence del dot f. I thought there were 4. What am I thinking? Okay, that's it. There's 3. I don't know why. Okay, gradient, divergence, and the last is what we have is the curl. So again, suppose that we have some function f. What I'm going to do is take the cross product of the del operator and f. Now, I'm not going to work it out all the way because it's just a summary video. But to do that, what we do is take the determinant of x hat, y hat, z hat, and then I'd put my components of my del operator, partial with respect to x, partial with respect to y, partial with respect to z, and then I'd put my components of my function fx, fy, fz. And then you do the determinant would just be, x hat's going to be the partial of fz with respect to y minus the partial of fy with respect to z for the x component, and blah, 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 blah. Okay, so that's the other one. So gradient, divergence, curl. So the curl tells you how, it seems silly to say this, but it's true, how curly a field is. Imagine a vector field where it like swirls around. It's the amount of swirliness. And so magnetic fields, due to currents and moving charges, have curliness. Electric fields, due to point charges, diverge. You'll see it. Okay. Next. See, I'm flying through this. There are second derivatives. I'm going to write down just one of them because it does come up, and I can't remember it. I forgot it already. So we have this. We have the curl of f. So I can take the curl of the function f and then take the curl of that resultant. Remember, that gives me a vector. This gives me a vector. This gives me a scalar. This gives me a vector. Okay. You can do this, and it turns out to be equal to this. Del of del dot f minus del squared of f. Now, this is we call the vector Laplacian. In Cartesian coordinate, it's just using the second derivatives. But here we have the divergence and then the gradient of that. So this does give me a vector. That's a vector too. This just comes up. But if you want, and you should know that there is a book, this book, and in the front they have right here second derivatives. So you don't have to remember them. They're in the book. I didn't derive them. I wouldn't remember them or anything like that. So that's that. Where am I at right now? I guess we're on line integrals. So we have a line integral. The classic from previous classes is work. Work is the integral of f dot dl. Now, in your intro physics class, you did the simplest works you could do. Straight line, constant forces, simple things like that. But here it could be much more complicated. So imagine I have, something like this. I'm going to do the work along that path from A to B. So this would be A to B. The first thing is, in Cartesian coordinates, this path length, dl, is going to always be the vector dx, dy, dz. Now, that's not true in other coordinate systems, but in Cartesian coordinates it is. So then if I have a vector function f, I can take the dot product, and I'll get 3 terms, right? Now, so you could get 3 integrals. The other thing that you need to do, don't do what I've done. I'll just tell you in a second. Now, suppose I have this as the xy plane, and so I want to go along that path. That path is a function. I could say x squared plus y squared equals r squared, and I can use this to get relationships between dx, dy, and dz. So I could take the derivative and get dx's in terms of dy's, and then I can plug it in my integral and make every integral that you have, it could be more than one, has to just deal with x's, has to just deal with y's. So you have to convert things over to x's and y's and use that equation right there. Now here's what not to do. Suppose you're integrating from here to here and you're going that way. Don't say, oh, dl is negative dx 0, 0. Don't do that. That's what I did. The direction comes from the limits of integration, not the dl vector. Okay, I made that mistake. That's what I'm telling you. Next, we have surface area integrals. Now, I'll be honest. So let's say we want to calculate the surface area integral. I'll use flux E dot n hat dA. So you have to, if you have a vector field, is which we normally do, you have to take the product of the vector field with a unit vector. Look at that, balloons. I didn't say anything. What are the balloons? Balloons. Balloons. Balloons? Oh. This is a unit vector perpendicular to the surface area. So remember, it doesn't have to be a flat surface. It could be curved or something like that. So that does have to take into account. And then this would technically be a double integral. But it can be really complicated, because if you're integrating over a bubble, then it's going to be in the x, y, and z plane. So it gets really complicated. In general, if I'm in the xy plane, dA would be dx, dy, and so forth like that. Now, the book does write this as E dot dA. No, it uses lowercase a. I like this separate. The n hat is a part of the surface. It's from the surface, and then dA is for the coordinate system. So I like to separate them out. But you do you. Oh, I did miss something earlier talking about notation. So this is one of the things that, imagine that I have a charge right there, and I want to find the electric field right there. So I would call this RQ, the location of the charge, and I would call that RO, the location of the observation location. And then I'd call this R. So R would be RO minus RQ. I like to use the subscripts. Now, the book uses something weird. Instead of R, it uses script R. Instead of RQ, it uses R prime. I don't like R prime because I don't like to have two hats, right? You have two hats on that. Sometimes you have to do two hats. But the vector arrow and the prime arrow, you know, the book uses bold face. You're not going to write bold face on your paper. So I don't like that. But that's that. So when you see that, know that. Now, the other thing, when we get to a volume, see the same thing up here. I'm telling you the differences in the way I do it and the way the book does it. For a volume integral, again, we're going to have some function. Let's just say A is the volume integral of f dv. So dv, you have to integrate over all three directions. Oh, for the surface area integral, I mean, don't freak out, because you're only going to have situations where it's trivial to do. Okay, we're not going to do super complicated surface area integrals. And the same thing is mostly true for volume, not 100%. For a volume integral in Cartesian coordinates, dv would be dx, dy, dz. And then here the book uses this as d tau. I think because they don't want to call, they want to say v for potential, the scalar electric potential, and so they use tau. I don't like that. I use dv. Okay. Now we have two very important things, not going to derive. They come up a lot, and they are the divergence and Stokes theorem. So the divergence theorem says that, actually I'm trying to, yes, the integral of del dot f dv is going to be equal to the surface, and this is over a volume, but you know that because it's right there, is going to be equal to the closed path surface area integral f dot n hat dA. So whenever you see that, any vector field f, okay, this is Gauss's law for electric fields, right? Because the divergence of the electric field, I'm trying to think, is the total, that is Gauss's law, right? Yeah. That's the total charge inside. We'll see that later. But that's how you get, this is the flux. Okay. And that's a closed path integral. Now, we always write just one integral. We know that's a volume integral because of dv over here. We know this is surface area integral. And this is a closed surface that bounds that volume. So they're related. And then we have Stokes' theorem, which says that del cross f dot n hat dA, a surface area integral, is equal to a closed path integral of f dot dl. That's right? No. Yeah, that's right. So this is the curl of some product over some surface area, and this is a path bounded that bounds that curve. So that's Stokes, and this is the divergence theorem. Again, you use those a lot. You don't have to memorize them. They're in the book, in the front cover. Okay, now we have just a few more things, right? Yep. So all we have to do is talk about spherical and cylindrical coordinates. You would not believe how much you use spherical and cylindrical coordinates. So let's see if I can draw this. I can use my colors here. So let's say I have the z-axis, and then I have the y-axis, and then I have the x-axis. So this is x, z, x cross y is z. Oh, I got that color wrong. This is why you shouldn't use colors. Okay. So I can determine the location of some object in Cartesian coordinates. The vector r is just going to be x, y, z. So those are my parameters. I'm not going to use the color chalk again. We need 3 coordinates to determine the location. In spherical coordinates, we have the coordinate phi, and then we project this down into the xy plane, and then we have the angle theta, and then we have the length r, which is not a vector, it's a coordinate. So x, the x coordinate, what we do is project down into the xy plane and then project over the x-axis. So this is r, that's theta, so this is r sine theta. And then I project over and I get cosine phi. Y is r sine theta sine phi, and then z is r cosine theta. So you hopefully have seen that before. Now, what you may not have seen is the unit vectors. Okay, so in Cartesian coordinates, we have these unit vectors x hat, y hat, z hat. I can write it that way. That's true. That's right. In spherical coordinates, we have the unit vector r hat, and in the direction of changing r, we have the unit vector phi hat, and then we have the unit vector theta hat. Wait, this is backwards. That's theta, and that's phi. That is an important point that I made on purpose. I made that mistake on purpose because in many math books, this is the angle phi and that's the angle theta. In most physics books, this is the angle phi and that's the angle theta. So just be aware of which one you're using. I wrote those correctly though. So that would be theta hat, and then this is going to be phi hat. We need the unit vectors in terms of Cartesian coordinates. It turns out to be very useful. So the r hat vector is equal to, in Cartesian coordinates, it is sine theta, cosine phi, sine theta, sine phi, cosine theta. And you'll notice the key thing here is that they're not constant unit vectors. The Cartesian coordinates are constant. They don't change as you move around. Now, I'm not going to do the theta hat one, but it does turn out that the phi hat one's very useful. You can look them up, and they're in the front of the book. Phi hat unit vector is going to be negative sine phi, cosine phi, 0. That one comes up quite a bit. Another thing in spherical coordinates are the differential elements. Right? Instead of dx, dy, and dz, we have these d, l, r. This is the change in length in the r direction. It's going to be dr. And then we have the change in length in the d theta direction. d, l theta is r d theta. And then, because it's just the arc length, right? Because we're moving this way. It's the arc length as you move back and forth into the d theta direction. And then dl phi hat, well, we have to actually project down into this plane. So we have the r sine phi, sine theta, and then d phi. So if I want a path integral in there, I may have to use one of these. If I want a surface area integral for a sphere, well, my dr is not going to change, so I have dl theta times dl phi, and I get the surface area element. If I have a volume element, I multiply this by this by this. So those are important to at least see. If you don't remember them, it's fine. Finally, we have cylindrical coordinates. These are pretty easy. It's just using phi for the xy direction and z for the z direction. And then so we have, I'm just going to write down the unit vectors in cylindrical coordinates. R hat is equal to cosine phi, sine phi, z hat. Is that right? No, there is no z. Yeah, because it's in this way. So that's 0. And then phi hat is going to be negative sine phi, cosine phi, 0. And then z hat is z hat. That's that. Okay, like I said, there is a ton of stuff in Chapter 1. And, you know, a lot of physics courses, you would have a course called Mathematical Methods of Physics, and they cover pretty much half of the course is that chapter. So don't feel like you have to understand everything. You may want to reference back to that chapter when you get to things that you're not sure about. That's what I would recommend. So there you go. Chapter 1, I'm going to have Chapter 2. My whole playlist for my electrodynamics course is down below in case you want to see that. I'll talk to you later.